Welcome to this explainer. Okay, today we are taking our physics knowledge and graduating from simple little dots into the incredibly dynamic, realistic world of rigid bodies. Up until now, we've kind of looked at objects in this idealized way, right? Treating them as if they were just a single tiny point in space with absolutely no actual size. But let's be real, any actual body we encounter in our daily lives, whether we're talking about a spinning top, a ceiling fan, or even a tumbling gymnast, it has a finite actual size. So to really wrap our heads around how the physical world moves, we have to look at these extended bodies as a whole system of closely packed particles. It is literally a game-changing shift in perspective.
Here's our quick roadmap for today. We're going to start by moving beyond the point mass. Then we'll check out the types of rigid body motion, define what exactly a center of mass is, explore symmetry in continuous bodies, and finally, track the actual motion of that center of mass.
All right, let's kick things off with Section 1, Beyond the Point Mass.
So, here's the big question. How do we calculate the trajectory of something that spins, warps, or maybe even breaks apart mid-air? Like we just mentioned, treating objects as sizeless points is easy, but real life is just way more chaotic. Think about it for a second. If you grab a heavy textbook and chuck it across the room, not that I'm recommending that, it doesn't just glide in a perfectly straight line like a tiny dot. No way. It rotates, the pages flutter, and the different corners of that book are moving at completely different velocities at any given instant. So how on earth do we make sense of a system where millions of individual particles are all just doing their own thing?
To solve this massive headache, we use a new model, and it's called the rigid body. In a perfect world, a rigid body is an extended object with a perfectly definite and completely unchanging shape, meaning the distances between all the pairs of particles inside that body never ever change, no matter what you do to it. Now sure, in the truest sense of the word, no real physical body is perfectly rigid, right? Everything deforms at least a tiny bit under force. But for things like car wheels, massive steel beams, or literally entire planets, that warping or bending is so incredibly negligible that we can confidently just treat them as rigid bodies.
Moving right along to Section 2, Types of Rigid Body Motion.
Okay, take a look at this ceiling fan. It's a perfect example of pure rotation. Notice how every single particle in those fan blades is moving in a perfect circle, totally perpendicular to a stationary axis. Because the pivot of the fan is completely fixed to the ceiling, it's constrained. It obviously can't translate or slide across your living room, so its only possible motion is just to spin. Every single particle on those blades traces out a circle, and if you find the center of all those circles, they line up exactly on the axis of rotation. And here's a cool little detail. Any particle sitting directly on that axis has a radius of 0, which means it remains completely stationary while the rest of the fan whips around it.
But what happens when that axis isn't nailed down? Picture a solid wooden cylinder rolling down a grassy hill. This is not pure translation. If it was pure translation, every single point on that cylinder would be moving at the exact same velocity at any given instant, kind of just sliding down together. But because it's rolling, the particles are actually moving at entirely different velocities. In fact, get this, the exact point of contact with the ground actually has a velocity of 0 if it's rolling without slipping. So rolling is this beautiful complex combination of two things, the entire body translating down the hill, plus the body simultaneously rotating around its axis.
Which brings us perfectly to Section 3, Defining Center of Mass.
To make sense of this combined sliding and spinning motion mathematically, we've really got to find the system's perfect balance point. And don't worry, we don't need to get bogged down by overwhelming equations here. We literally just scale up the mass-weighted average of distances. We start on a simple 1D line. If you have two particles, the center of mass is just the mass-weighted mean of their positions. If they weigh exactly the same, boom, the center is exactly halfway between them. Add a third particle, now we move into a 2D plane and calculate the x and y coordinates. And for a full rigid body, we just generalize this to n number of particles scattered across a 3D space, summing up the mass times the position for every single particle in the whole shebang.
So here is the absolute crucial point. If you place the origin of your coordinate system exactly at that center of mass, the vector sum of all those mass positions equals exactly 0. 0. It's the ultimate perfect point of equilibrium for the entire system. Basically, we can take all the mind-boggling complexity of a massive rigid body and mathematically condense its total mass down into this one, single, incredibly elegant position vector.
All right, Section 4, Symmetry and Continuous Bodies. Let's see how this scales up.
Now, because there are literally way too many atoms to count in an everyday rigid body, like, say, a meter stick or a heavy flywheel,
We definitely can't do a discrete mathematical summation for every single microscopic particle. Nobody has time for that. The spacing between the atoms is just so incredibly tiny that we can treat the whole body as a continuous distribution of mass. To pull this off, we just mentally subdivide the body into an infinite number of infinitesimally small elements of mass. As we make the number of elements bigger and bigger and the mass of each little chunk smaller and smaller, our approximation actually becomes mathematically exact.
Take a look at this table. It perfectly shows this super elegant mathematical transition we make. Those chunky, discrete summations smoothly transform into continuous integrals. Instead of using that big Greek letter sigma for summation, we literally just swap it out with the integration symbol. We integrate the position, multiply it by the tiny mass element across the entire body, and then just divide by the total mass. Guys, it is the exact same concept as the discrete particles. We're just adapting it for a solid, unbroken object.
And oh, you're going to love this. Here is a fantastic, absolute mind-saver of a shortcut. If a continuous body, like a uniform rod or a ring or a perfectly round sphere, has reflection symmetry, you don't even need to use calculus at all. No way! The center of mass is simply its exact geometric center. Think about a completely uniform thin rod. For every tiny little element of mass on the right side, there is an identical, perfectly matching element of mass mirroring it on the left side. Because of this reflection symmetry, their mathematical contributions perfectly cancel each other out. The net result? The center of mass sits perfectly at the origin, right at its geometric center. I mean, how incredibly convenient is that?
Okay, moving to our final section, Section 5, Motion of Center of Mass.
So, now that we've found it, how does this magic center point actually move through space? Well, Newton's second law steps in beautifully right here. The center of mass moves as if the entire weight of the whole system is concentrated exactly at that one single spot, and as if all the external forces in the world are applied directly to that exact point. By taking the derivative of our particles' velocities with respect to time, we find the acceleration of the center of mass. And when we multiply the total mass of the entire system by that acceleration, it equals the exact vector sum of all the external forces acting on the system. It's brilliant.
So the really crucial takeaway here is that you absolutely do not need to know the complex internal forces tearing a system apart just to predict where its center of mass is heading. Remember Newton's third law. It tells us that internal forces, the particles inside the body pushing and pulling on one another, they always occur in equal and opposite pairs. They cancel each other out entirely. Therefore, all that internal chaos contributes absolutely zero to the overall motion of the center of mass, literally nothing. Only external forces, things like gravity or friction, hitting it from the outside can actually change its trajectory.
Imagine a firework exploding high up in the midair. This is honestly so stunning to visualize. You have this projectile flying through the night sky, being pulled down only by the external force of gravity. Then, suddenly, boom, it fragments into hundreds of pieces. But because that explosion is purely internal, the total external force acting on the whole system hasn't changed at all. The individual brightly colored fragments might be scattering wildly in every possible direction, but if you magically calculated their collective center of mass at any given microsecond, that invisible mathematical point would still be gliding along the exact same smooth, highly predictable parabolic curve it was on right before the explosion.
So the next time you see an Olympic gymnast tumbling through the air, try to look past the spinning limbs and the twisting torsos and see if you can spot that perfect, invisible parabolic arc. No matter how much they twist, warp, or flail their arms around, which remember are all just internal motions, their center of mass is strictly bound by the external force of gravity, tracing a beautiful, mathematically flawless curve through the air. But it leaves us with a really fascinating thought, doesn't it? If every tumbling athlete, exploding firework, and even shattering asteroid out in space follows this exact same invisible law, what other hidden, predictable balances are quietly shaping the chaotic universe all around us? Thanks so much for exploring this explainer with me.